Alright, so let's continue from this relation. We have already seen, after defining the radian measure for angles, that 180 degree is equal to pi radian. So using this, one can convert degree measure into radian measure and radian measure into degree measure using these things. Okay. Because 180 degree equals pi radian, so 1 radian will be pi over 180 degrees, and that approximately is equal to this. Now, if you want, you may use this approximation in place of pi. Which is what we normally do. Okay. But you can also use some other approximation. You cannot, of course, use the entire value of pi, since that is irrational. So normally when we calculate with pi, either we keep pi as pi or we use some kind of rational approximation. If you use this rational approximation, you will not get exactly this value, but something close to this. I have calculated this on a calculator. So that's why I am getting this. So what you do here basically, if you use a calculator, say you divide pi by 180. On the calculator you do this. You are going to get a figure like 57 point something. Some digits will come. Okay. Then what you do, you take 57 apart, whatever is left will be 0 point something. You multiply that by 60, because whatever you are going to get 57 point something degree. That means 57 degree plus 0 point something degree. To turn that 0 point something degree into minutes, you multiply by 60. That will give you 17 point something minutes. From there you take apart 17 and you will be left with 0 point something minutes. You multiply that by 60, then that will give you 44.8 something seconds, from where I have kept 8. Okay. Similarly, 1 degree is pi over 180 radian, which approximately is equal to this much radian, 0.01745. This is the symbol for approximately equal to. Okay. Now we of course are never going to use these values for our conversions from one unit into the other, but we will use this relation itself. Keep in mind, we are going to use this relation and this relation. They are both coming from that same equation, but not the approximate values. These are just values that tell us how much of each unit is in terms of the other, roughly. Okay. So now using this relation, let us see some radian measures of some known angles in degree. For example, some of these are given in the text. You are already familiar with this, but let's see once more. Say 30 degree. To turn 30 degree into radian, what do you have to do? You multiply by pi over 180. And that gives you this. Radian. If you simplify this, it becomes pi over 6. So pi over 6 radian. Similarly, you will see that 45 degree is pi over 4 radian, then 60 degree is pi over 3 radian, 90 degree is pi over 2 radian. There are some other angles also beyond 90 that is given here, that has been considered here, 180. For this you do not even have to do anything because you already have it here. So this is pi radian. Then there is one more angle, two more angles. 270. 270 means 3 times 90. That means 3 pi over 2 radian. And then there is one more, the complete revolution, 360 degree, that is equal to 2 pi radian. Recall that actually this is what we found first, that 360 is equivalent to a complete revolution, a full rotation, and in radian measure that is the same as 2 pi radian. From this relation only we got this relation, and from there we are getting everything else. Now there is a notational convention which sometimes we use while writing angles in radian measure, and the convention is that we do not write radian. In other words, say I want to write this equation, say 45 degree equal to pi over 4 radian. Usually it is written like this. Is equal to pi over 4. We do not write the radian unit, but we have to write the degree unit. The convention is that since we will be using radians more and more, so it is convenient to make the convention to not write radian. Whenever you say that something is an angle, not necessary, it's not necessary. See, you may think that whenever you have the radian measure of something, pi has to appear. No, that is not necessary. Pi may not appear. For example, you have 1 radian. The convention is that you do not write the name of the unit radian. It is to be understood that whenever we talk about angle and we just write the numerical value itself. Numerical value means, of course, with plus minus sign, if minus is there, then it is in radian. But if you suppress the name of one of the units, you have to write the name of the other unit. So if it is in degree, we write that circle, small circle. Okay, so that is the convention. But we do not stick to this convention like we have to always use it. Sometimes we do write radian, sometimes we do not write radian. It's up to us. So if you see something like this, you have to understand that on this side, because there is no unit, it is in radian. That's the convention. Now let's see some examples involving these conversions. Example 1. So the first two examples are going to ask us to simply convert an angle from one unit into the other. For example, this one, convert 40 degree 20 minute into radian. (40 degree 20 minute into radian. You already know that in any such conversion, not just from degree into radian or radian into degree, but in any kind of conversion, you have to first of all make the value or change the value into one unit. Here there are two different parts of the unit degree. I mean, of course, you have degree, but you also have minute. So you turn that minute also into degree. Take everything into degree, and then only you can convert, because we have the relationship between degree measure and radian measure, not minute measure and radian measure. If one wants, one can find that relation, but there is no need. Okay, so we turn minute into degree and then only we convert. So the solution is going to go like this. We have 40 degree 20 minutes. This actually really is 40 degree plus 20 minutes. To turn minute into degree, what will you do? Because 1 degree equals 60 minutes, so you divide by 60. And the moment you divide by 60, the unit changes to degree. That means this equals 40 plus 1 over 3. A question comes into our minds, why do we need a new unit? Is it just for the sake of introducing some new unit because it looks very peculiar, no? Radian. It will become clear when we start studying calculus. While doing trigonometry, you may fail to appreciate the need for considering this unit radian. But when doing calculus, you will see that there also we will have many occasions to consider angles. There we will see why radian measure is more convenient than degree measure. We will see the actual reason for that. The reason is a specific limit. We will see what limits are, what all these things have to do with radian. But right now, let's do this. Plus 1 over 3 degree. That means this will be how much? 121. Now that everything is in terms of degree, so we can now apply our relation and turn this into radian. To do that, we have to multiply by pi over 180. Now in this type of problems, if you treat it as a problem for which you have to write a solution, it's better to not follow that convention of not writing radian, because you have been asked to convert one unit into the other. So in a sense, it's better to write that unit, because that's what we want, right? So this is one place where we won't follow that convention. So we simply write radian. If you want, you can write simply RAD, shortening it somewhat. I don't know if that is really allowed from an examination point of view, but it is a practice. Okay, it's not something that simply I am making up and saying no. We do write RAD. Now if we simplify this somewhat, won't really be simplified because we have 121. No cancellation is possible because the only prime number which divides 121 is 11, and we do not have any 11 factor here. 11 is not, of course, there in 3, and 11 is also not available in 180. So we simply multiply and get 540. If you want, you can use some approximation of pi to calculated numerical value here, but usually we keep things like this. Whenever we encounter pi, we just keep pi as pi, and we do whatever else we can do with the rest. Next example 2. Here of course we have to do the opposite. Convert 6 radian into degree. Into degree. So this is simpler than this one. Here radian means just radian. So we can straight away convert. We have six radian equals 6 times 180 divided by pi. Recall what I told in the previous video about how to remember these numbers by which you have to multiply. When you turn radian into degree, put the degree part above the radian part. And by degree part and radian part, I mean the two sides of the relation 180 degree equal to pi radian. Here we are converting into degree, and 180 is on the degree side. Pi is on the radian side, so the degree side gets preference. That's why 180 appears above pi. That way you can remember, okay, easily. So how much is it? Let me see once more. Okay, I am infamous for making this type of mistakes in actual calculation. Yeah, I think it's correct. In the book, some approximation has been used. Yeah, I think 22/7 has been used in place of pi. However, I am not going to do that. Okay, let me keep it like this. And do not forget, I myself forgot here, the moment you have converted, you write the unit, that is degree. If you use 22/7, which is not anything wrong, but you won't get the exact value, you will get an approximate value. So if you write, say you want to continue this, okay, so after that you are going to write 1080 divided by 22 divided by 7, but there do not write equality sign. Do not write equal sign, write this approximately equal sign. After you write approximately equal sign, then whatever calculation you are doing, there you continue to write equal sign. So that sign alone will take care of the fact that the original value is not equal to whatever you are now getting. It's only approximately equal. Example 3. Next. Now we are going to see that relation also. You remember that while defining the radian measure, we in fact invented means the definition itself gives us a new relation, a relation between the radian measure of an angle at the center of a circle, the arc length of the arc that the angle gives us on the circle and the radius of the circle. Based on this relation also you will likely get some problems. The only thing you have to remember is that in this relation theta has to be in radian. If you write degree here, no, then this is wrong. So the next example is about that relation. Find the radius of the circle in which a central angle of how much? 60 degree intercepts some circular arc. The angle is going to intercept on the circle an arc of length 37.4 meter. Okay, so here the situation is like this. If you want, you can draw a figure. In fact, also for your understanding only, you can make the figure a part of the solution. Do not forget that when you draw a figure on paper, always use pencil, don't use pen. That's the rule, and that also saves you from making if you make any mistake, you can then use the eraser to get rid of it, okay, to rectify it. Also, while drawing circles, use compass, you use your geometric box tools. So the thing here is this: there is some angle whose vertex coincides with the center of some circle. Find the radius of the circle. So we need to find this R, that radius, in which a central angle of 60 degree intercepts an arc of length 37.4 meter. So this is the arc length S, and the things we have here are theta equal to 60 degree, R has to be found, S is 37.4 meter. You do understand that you should not write exactly like this. You have to write in words the things that are given, that you have to find the radius, all those things you have to write. Okay, I am not going to elaborate on that, since that is just about language, about which you already know. So instead, let us do the problem. Note that here we have the three ingredients, among which we have to find R. We are given theta and S, but the important thing to note here is that theta is not in radian. So you have to first convert it into radian, and then only you can use the relation that theta equals S over R. If you simply write 60 degree equal to 37.4 divided by R, that is wrong. So then you write converting theta into radian, we get all those things will give you this. So you multiply by pi over 180, usual stuff, pi over 3 radian. If you want, you can write radian here, or you may also choose to not write. Okay, you can use the convention. You can simply write 60 degree equal to pi over 3. Since converting degree into radian is not our main aim, so it's okay to not write radian here. So now we know that theta is equal to S divided by R. So this gives you R is equal to S divided by theta. So that's how we can find R. So if you now use the values, you are going to get this. S is 37.4 divided by pi over 3. Now if you again, if you want to use some approximate value for pi, you can do that. Otherwise, what you can do, you keep pi as pi, take that 3 and multiply that with the numerator and get whatever you will get. Okay, so I am not going to do that. So you will have something here. And do not forget to ultimately write the unit of R, which is meter. Since the arc length is given in meter, so radius should also be in meter. And that's it. That's the radius. Okay, so this was example 3, no? Yeah. Next, example 4. This one is quite interesting. Example 4 tells us the minute hand of a watch of a watch is, its length will be given, I think. Yeah, 1.5 centimeter long. Alright, then how far does its tip move in 40 minutes? Okay, so it's also a situation like that only, except here we have motion involved. It's nothing static. The minute hand is always rotating, it's moving. So the tip is moving along a circle, along the rim of the watch, whatever it is. So we are given what here? We are given R. Do we know about theta? Yes, we know about theta. And that will, actually we do not know about theta, it's not given to us in the form of theta, something else is given. 40 minutes. 40 minutes. So in 60 minutes, the minute hand makes one complete revolution. So in 40 minutes, how much revolution it will make, that we can calculate, since the minute hand, let me write the things in words for this one at least, of the watch makes a complete revolution in 60 minutes. In other words, in 60 minutes it moves 360 degrees, or it rotates 360 degrees. In 40 minutes it will make 40 divided by 60th part of a revolution, complete revolution. So what does it mean? What angle is this? i.e., it rotates by an angle of, so this means 2 over 3 times 360 degree. So we can calculate, we can simplify this. So if you simplify, what will it be? If you divide 36 by 3, you get 120, so 240 degree. But the kind of thing we are going to use, that relation, that needs radian measure. So you have to now here itself, let us convert this into radian by multiplying it by pi over 180. Can we simplify this? 6 is a common factor. So if you divide the numerator by 6, the 0, 10 of course gets cancelled, then we are left with 4 in the numerator. And the denominator will be what? 3. Actually I should have written radian here itself, but you understand I do not have space. So you write that. So that means the angle by which it rotates, the minute hand, is 4 pi over 3 radian. So this is our theta. And again, if you do not want to write the unit, you can simply write like this. I will, however, write the unit to emphasize the fact that whenever we use the relation theta is equal to s divided by r, theta is in radian. And what else is given to us? The length of the minute hand is given, that means r is given. Also, r is 1.5 centimeter. So the tip travels a distance that is equal to the arc length for this angle, right? So the distance the tip travels in centimeter is s. So s over r is theta. That means S is equal to r theta. So 1.5 times 4 pi over 3 centimeter. In centimeter we have already written. So what will it be? 1.5 is also 3 over 2. That means 2 pi centimeter. So it moves by a distance 2 pi centimeter. Here also you can give some approximation for pi, or you can just keep it like this. And finally there is this fifth example. If two arcs of same length in two, okay, so now we have two circles. If two arcs of same length in two circles in two circles, on two circles, whatever you, however you want to write, you write. The meaning is understood. Subtend angles (65° and 110° at the center. Oh, we started with if, no? So it will continue. Then find the ratio of their radii. All right. Let the radii be R1 and R2. If I simply write like this, is it becoming clear that R1 corresponds to 65 and R2 corresponds to 110? No, it is not clear. So you have to write somewhat differently. Let the radii of the circles at whose centers the two arcs of same length subtend angles. We have to write a lot, but there is no other option. Subtend angles 65° and 110° be R1 and R2 respectively. Okay, and again Here the angles are, I think, purposely given in degrees so that the student, if the student forgets to convert it into radian, that's it. Although here actually nothing will go wrong, but it's wrong to use that relation when the unit is degree. Nothing will go wrong in this specific example because of something. Okay, the type of the nature of the problem is such that even if you use simply degree, you will get the correct answer, but the method will be wrong. Hence, so for both the circles we have the same S. Actually, you will have to write many other things. Okay, let S be the length of that, the common length of the arcs, but I am not going to write all that much. So we know that S is R1 theta 1, but at the same time S is also R2 theta 2. From these two equations you get R1 theta 1 is equal to R2 theta 2. Note that I have also not said what theta 1 and theta 2 are, but you do understand that they are the radian measures of these two angles respectively. So that means this is 65 times pi over 180. That is theta 1. And on this side we have 110 times pi over 180. Actually, pi over 180, the two pi over 180s cancel out. That is why I was saying that even if you use the degree measures themselves, you won't get wrong answer. And this gives us, after cancelling that common term, R1 divided by R2 equal to 110 divided by 65, where I think, yeah, because both the numerator and denominator are divisible by 5, so further simplification is possible. So if I divide the numerator by 5, what I am going to get? 5 times 2 is 10, another 2, so 22, and dividing the denominator, I get 13. Yes. So the ratio of the radii is 22 is to 30. That is, you have this. And again, when you write an actual formal solution, say on exam paper or somewhere else, you do not write straight away from this, you do not write this. You write hence the ratio of the radii of the circles, whatever you want to write, is this. Okay, and that's where the solution ends. And this is where this small section also ends. After that we have a small exercise set that we will solve this coming Thursday. And after that only we will see the extension of the definitions that we were talking about in the last video. In fact, let me just tell you roughly what the extension is. It's nothing really that complicated. Once you realize what it is, it will be extremely easy. The thing is this. So you now have an angle for which you have to define sin theta. So let's just concentrate on sin theta first. So what you do, you draw your usual x and y axis. Okay. the positive directions of x and y axis. Now the angle, of course, now for us angle corresponds to a rotation. So we are considering rotational angles. We are no longer restricting ourselves to only geometric angles. That means our angle has an initial line and a terminal line. What you do, you put the angle in this coordinate plane. First of all, you have the angle. Okay, so it's like this. After going through whatever rotation the angle corresponds to, you put that angle in the coordinate plane in such a way that the initial line of the angle coincides with the positive x-axis. Okay, first you do that. Originally the angle may be in whatever way it may be imagined, but you can rotate the angle, the entire angle, you can rotate the angle and adjust it in such a way that the vertex of the angle coincides with the origin of our coordinate system, and the initial line is the x-axis, positive x-axis. Then the terminal line will lie wherever it lies. Say it lies here. Say this is the terminal line. Okay, this is the initial line of the angle, and this is the terminal line. And I am also not necessarily talking about an obtuse angle. Maybe that this terminal line has gone through many full rotations and then only it has come here. Also, keep in mind that actually I may be talking about this angle also. That is why it's not enough to simply draw the initial line and the terminal line. You have to also show the rotation. Say this. Say this is my angle, rotational angle. Okay, and say the angle has measured theta, either in degree or radian. It does not matter. Say it is theta. Now what is sine theta? So what we do, we draw a circle whose center is the origin and which has radius 1. Such circles are called unit circles which have radii 1. But specifically, if you consider such a circle whose center coincides with the origin, that is sometimes called the unit circle. So we have drawn the unit circle here. Now, on the coordinate plane, the terminal line, whatever its position is going to intersect the circle at some point, obviously. And that point will have its coordinates, right? Just like any point on the plane has coordinates, that point will also have its coordinates. Consider this y. This y is what we define sine theta to be. Sine theta by definition is y. In other words, we are defining this trigonometric function value, sine value of the angle theta, as the y coordinate of a point. Similarly, that x is what cos theta means. The meaning of cos theta is x. This may look very strange at first. How is this definition related to the original existing definition where we have, say, acute angle? You will see that this definition nicely extends the original definition in the sense that instead of considering an obtuse angle or say a very large angle like this, if you really go back to your original situation where you have an acute angle where the rotation is just that, you will see that this new definition reduces to your old definition. In that sense, this is actually an extension. And the magical thing is that even in this general setup, all those rules, all those identities that we proved, we came across in our old definition continue to be true here. For example, we still have this. Even in this setup, in particular, you have things like this. Sine square minus 1000 degree plus cos square minus 1000 degree is still equal to 1, where previously this would have been meaningless. Already we do not have in the old definition angles this large, and also negative angles were meaningless already. But now that we have a meaning for all these angles, and we will see in more detail how this definition works, what its component parts are. We will see all those things in more detail in the next video. But we will also see that the existing things continue to be true here. See, that's what we aim for whenever we extend something in mathematics. Now, you have a situation where something happens. You want to extend its scope by defining something more general. In that more general thing, the existing something is only a part. Simply defining something more general is not really that big of a deal. It will become important if the things that you know about the existing thing, for example, this kind of relations, continue to be true in the general setup. Maybe not everything will be transferred to the general setup, but a majority of the things get transferred. Then it is a successful and interesting extension. And this is what we keep doing. We means the mathematicians do. Okay, we only learn. But we can say that we also do. At least we learn these new things. Okay, that's what we do in mathematics. And that's just it for tonight. After this, tomorrow what do we have? I forgot. Actually, I was not well, so I was not able to make videos these last 2 days. So everything went out of my mind. Something happened. But now I am well, so let's see tomorrow what comes. So that's just it for tonight. See you tomorrow. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.